work through Unit 6, the review worksheet for the exam. And remember that you have three equations that are going to be pertinent to this. They are for kinetic energy, equals 1/2 mv squared, and this is in kilograms, velocity in meters per second. Energies are always going to be in joules. Gravitational energy, mass times gravity times height, mass in kilograms. Gravity constant is 9.8 newtons per kilogram, or 9.8 meters per second squared. That's the same thing. And height in meters. And elastic energy, which is 1/2 k delta x squared, where k is the spring constant, and delta x is the displacement. So problem 1 has a question where we have two springs, one a little stronger than the other. Spring 1 has a spring constant of 10 newton meters, and spring 2 has a spring constant of 8 newton meters. And in question A, we want to know how much elastic energy would be stored in spring 1 if it was stretched from 0 to 0.4 meters. So it's simply a matter of putting in the elastic energy formula equals 1/2 k delta x squared, plugging in the numbers 1/2, and our spring constant is 10 newton meters. And our displacement is from 0 to 0.4, so that's simply 0.4 meters squared. And if we plug those numbers in, we come up with a value of 0.8 joules. In question B, we want to know how the amount of energy stored in spring 2 would compare to spring 1 if they're stretched the same distance. So everything being equal, which one stores more energy? And so spring 2 has spring constant of 8 newtons per meter. And so you can see that if I went down here, and this is spring 2, it has a spring constant of 8 newtons per meter, and that would going to go in this spot here, that the whole value would be less. So less value for spring 2 because it's got a smaller spring constant, and the spring constant tells us how much force it takes to stretch that spring a certain distance. That's the newtons over meters. And because the spring constant is smaller for spring 2, it will hold less energy. And you could calculate it out if you want to. It's fairly straightforward from the other one. And it comes out to 0.64 joules. In problem 2, we have a 1.5 kilogram kitten jumping down from a 2-meter high fence. For the problems that we're doing these equations for, generally we're going to ignore friction, so we don't have to worry about dissipated energy unless we're told to. And in this problem, we want to draw pie charts for how the energy is stored before the kitten jumps, as the kitten is falling, and just before the kitten lands on the ground. And with the pie charts, we don't know exactly how much sometimes each pie slice is. We're just looking for a general trending in the size. So we're going to do 3 pie charts for this one. I'm going to change color here because I don't like the black, or don't like the red rather. And so we'll put in a pie chart for the beginning, a pie chart for halfway, and a pie chart for just above the ground. So beginning. Okay, so the energy the kitten has just before it jumps, and you might be tempted to put chemical energy in because the kitten is jumping here, but really what we're talking about is the kitten just kind of falling downward. So we don't have to worry about the kitten jumping up first. We'll make this one a little simpler. And because it's not jumping upward and exerting energy, we won't have to worry about chemical energy. So the energy in the beginning state is strictly gravitational. It's got the potential energy from being able to fall. At the end, just before, the instant before it touches, that energy is all kinetic. And then if I went halfway, it's going to be about half of each. Half gravitational and half kinetic. For the second part of the problem, what will be the kitten's speed when it reaches the ground? So we want to know right here, what is its kinetic energy? Okay. I don't know, from the formula there, I need 1/2 mass times velocity squared. I'm looking for V. I don't have directly EK, but if I look at the pie chart, gravitational energy and the kinetic energy are the entire pie. So from that, Eg equals EK. So I can figure out gravitational potential energy because I have the mass, I have the height. So Eg is equal to, I'm just going to move things over here a little bit for more room, is equal to mass times gravity times height. And that's going to be 1.5 kilograms times the gravity constant of 9.8 newtons per kilogram times the height of 2 meters. And that works out to an energy of 29.4 joules. One to go in there. Okay. So the kinetic energy is 1/2 mv squared. So EK equals 1/2 mv squared, and that's also equal to Eg, so we're just going to make that equal to that value of 29.4 joules. So I'm going to solve for V. I'm going to basically kind of work out the mass for both sides, and then we'll do that. So this works out to 1/2. It's 1.5 kilograms times v squared. So what I'm going to do here is I'm going to multiply both sides by 2 to cancel out the half. I'm going to divide both sides by 1.5. Or, even better yet, why don't we simplify this first, and then we'll multiply both sides. So, move over here again a little bit here. So, I'm just going to do this. 29.4 joules over 1/2 times 1.5 kilograms is 0.75. So I'm going to take that and I'm going to put that over here. That's where the 0.75 came from, was 1/2 times 1.5 equals 0.75 kilograms over 0.75 kilograms times v squared. And if I do that, then v squared equals 39.2. And it's not cooperating with me. 39.2. That's going to be meters squared, second squared. That's not what I want. But if I take the square root of this, that's going to be equal to the square root of this. And V is going to equal 6.26 meters per second. That's my answer right there. And I ran out of the room there a little bit. Ran out of room, but that's my answer right there. 6.26 meters per second. Okay, problem 3. I went through and made things full screen, so we had menus here, so we can see a little more. I got a little more room to work. In problem 3, we have a 50-gram dart resting against a spring that's been compressed 0.05 meters. The spring then launches the dart straight up in the air. So we need a before and after situation here, and we need a conservation of energy equation. And so for our system, we're going to have spring, dart, and because we have this thing going up in the air and falling back down, Earth. And in position A, We have the dart resting against the compressed spring, essentially sitting on the ground. So no gravitational energy, it's not moving, no kinetic energy. These two would be just sitting at zero, and then all the energy would be inelastic. Again, unless these problems tell you otherwise, assume zero friction, and then that will kind of keep the problem a little simpler for us. And in position B, it wasn't really stated here, but if we started out with this dart here on a coiled spring, this would be A, and we have the dart going up and falling back down. And for B, we're looking for right here at the top of the arc. And so if we assume that's true, at the top, it's changing direction, so the velocity goes to zero for a split second, no kinetic energy. The spring has released, so no elastic energy. We're going to ignore friction for this problem, no dissipated energy. All the energy is going to be transferred to gravitational energy. All right. So this is assuming ignoring friction and assuming that we're measuring the dart at the top of the arc. Our equation then becomes elastic energy. We don't have a box for it, but we'll just put it in. Elastic energy is equal to gravitational energy. If 1.5 joules of elastic energy were required to compress the spring, what's the spring constant? Okay, so we're solving for K. So our formula starts out to be this, 1/2 K delta x squared. Now we want K. So we have the formula goes in to be 1.25 joules. Most of you like to put the numbers in, I've noticed, rather than solve the equation first, so we'll do that. Equals 1/2 times K times delta x. And so we've compressed it 0.05 meters, and we have to square that. Okay, and so we can simplify that a little bit. So 1.25 joules, 0.05 squared is 0.0025. And what we'll do then is we can take the half times 0.0025, or we can just leave them together and kind of transfer them both over to the other side. So what I'm going to do is I'm going to take this quantity times 2. So I'm going to take this 2 times that. That will get rid of the half. So this and this will cancel out. And then I'm going to divide both sides by 0.0025. Meters. All right. And that's going to equal K times 0.0025 meters squared over 0.0025 meters squared. And that will cancel. And if I do this math, then K will equal 1,000 newtons per meter. Part C, what's the maximum velocity of the dart after spring transferred its energy to it? Okay, and from the initial equation there, EE equals EG. That doesn't tell us anything, but the instant after the spring is released, EE is equal to EK. The spring transfers all of the energy from elastic energy to kinetic energy. So in this one, if I'd made an intermediate little bar chart, all of the elastic energy would have gone into kinetic energy. Again, we know that EE is 1.25 joules, so EK will equal 1.25 joules. We want to know V. EK formula equals 1/2 mv squared. We want to know V. And so we're going to go ahead and plug those numbers in. 1.25 joules equals 1/2 times mass. And here's where we have to be careful. It gives mass in grams. We have to have that in kilograms. So just very quickly in my head, 50 grams is 0.05 kilograms times v squared. And so what I'm going to do is I'm going to take both sides and I'm going to multiply. Essentially what I'm going to do is I'm going to take both sides over 1/2 times 0.05 kilograms. I'm multiplying by 2 divided by 0.05 is the way of looking at that. Equals this over 1/2 times 0.05 kilograms as v squared. I get that equal. All right. So that leaves me with 1.25 joules over 1/2 times 0.05 kilograms equals v squared. And when I plug all that in, and I take the square root of the answer on the left, I end up with v, well, anyway, I plug this in, v squared equals 500 meters squared seconds squared. And so what I'm going to do is take I'll take the square root of both sides, and that works out to, where am I at, 22.3 meters per second. And that is the velocity for part C. In part D, we want the maximum height the dart will reach. I had to kind of erase some of the stuff there because the writing won't go with Worksheet as a slide. From this one, elastic energy equals gravitational potential. And so we had, again, 1.25 joules equals mgh. And I can plug in the numbers I know. And so 1.25 joules equals mass, which is 0.05 kilograms, times the gravitation constant, 9.8 newtons per meter, times height. And what I'll do is I'll just divide both sides by this quantity here. So 0.05 kg times 9.8 newtons per meter, 0.5. Doesn't look any better. That's 9.8 newtons per meter. These cancel out, and I'm left with H equals 2.55 meters. If I do these calculations here, 1.25 over the quantity 0.05 times 9.8. In problem 4, we've got a 24 kilogram child descending a 5-meter high slide and reaches the ground with a speed of 2.8 meters per second. Do bar graph analysis for this equation. Okay, so we've got the child going to sit up on the top of the slide. Child is 24 kilograms. The height of the slide is 5 meters. And at the end, at point B, rider a little less out of control here. At point B, we're going to assume the height is equal to 0 and velocity is going to be 2.8 meters per second. Okay. That's supposed to be an M and an S here. So up here, height is equal to 5 meters, velocity equals 0. Okay, so in position A, velocity 0, 0 kinetic energy. No elastic condition here, so that's 0. We'll just make the entire graph gravitational energy. Our system is going to be child, slide, and birth. And in position B, there is no heights, no gravitational energy. We're going to have some dissipated energy here, and no elastic energy. So kinetic energy and dissipated energy are going to account for the amount of energy at the end. I don't know how much of each, so I can just guess. The child fell from 5 meters, so they're going pretty fast, and they're not going nearly as fast as sliding. What we could do is we could just assume F. That would be going the right direction. These quantities might not be exactly correct. But our equation then is going to be EG is equal to EK plus ED. So how much energy was dissipated? We're going to have to calculate that from the gravitational potential energy and the kinetic energy at the end. So our equation is going to work out to something like this, equals EG, that was all the energy in the beginning, minus EK, minus what energy was kinetic. All right, so let's go ahead and solve for that. I'm just going to solve them separately and just subtract them at the end. So at the beginning, the gravitational potential energy is fairly straightforward. That's mgh. Child is 24 kilograms. Gravity is 9.8 newtons per kilogram. Height is 5 meters. And when I run that calculation, EG is 1176 joules. Kinetic energy, which is the other one I need, is equal to 1/2 mv squared. I have all of those, so it's 1/2 times 24 kilograms times a velocity of 2.8 meters per second squared. And if I crunch those numbers through, I'm going to end up with 94 joules. So if I look at that, it looks like the amount of kinetic energy at the end, if I was to reset those bar graphs, the kinetic energy would be much smaller, dissipated energy would be much higher. So ED is going to be EG, which is 1100, erase your work here, 1176 joules minus 94 joules. And dissipated energy then is going to equal, the difference between those two, which is 1082 joules. So you see that that's going to be almost 10 times as big as this. So this original bar graph isn't entirely accurate. That if I was going to change that to make it more accurate, you don't have to do this. But the dissipated energy would be more like up here, and the kinetic energy would be just a little slice that was left there.